In this chapter, we will go into the basic scientific terms you need to be familiar with to understand this video.
The system of measure we choose should simplify, not confuse. To start off right, we should probably cite some terms we will frequently use. We're going to start off by talking about some basic terms and definitions. Depending on your background, you may be already familiar with these, but I want to make sure we all start off on the right footing.
We'll look at time, mass, gravity, weight, force, energy, power, pressure, torque, and vector. First is time. And fortunately, time needs no further explanation beyond what our intuition tells us. What about mass? There are lots of definitions of mass, but this one, the property of an object that resists any change in its velocity, is a pretty convenient definition. In these graphics, we show a baseball player standing on the earth getting ready to throw a ball. On the left, he's getting ready to throw a baseball, and the baseball has a mass of 145 grams. And on the right, he's getting ready to throw a lead ball. The lead ball has a mass of 19,247 grams. The baseball is going to be easier to throw because it is less massive, but the lead ball is going to be harder to throw because it is more massive. The baseball will travel much farther than the lead ball before they fall to the ground. Next is gravity. And for now, just our concept of gravity, seeing the force of gravity causing the apple to fall to the earth, is sufficient. And on to weight. Now, weight is the result of the force of gravity pulling on a mass, and weight is equal to mass times gravity. Here's our picture again on the Earth and then on the Moon. Same baseball, same mass, more gravity on the Earth, more weight. On the Moon, less gravity and less weight. On the Moon, we see a more or less straight trajectory. On the Earth, the ball will follow a downward arc because of the greater gravity. What about force? There are lots of definitions of force. Let's use this one: an interaction that changes the direction or speed of motion of an object. In both of these graphics here, I'm giving the ball motion by putting a force to it. Next is energy, and we'll spend just a little bit more time on energy. And we can think of energy as either the capacity to undertake vigorous activity or the capacity to do work. Now, with energy, we have an intuitive understanding. We say I'm full of energy, which means I can do things. I can go for a walk, I can go to work, or I can ride my bike. If we consider the energy necessary to climb a hill, the energy to climb a hill depends on the mass of the rider and the bike, the force of gravity, and the height of the hill. In fact, the energy required is the product of the three: mass times the force of gravity times the height. Now, interestingly, energy is what's called a state property, which means it depends only on mass, gravity, and height. And specifically does not depend on the grade of the hill, the speed at which I climb the hill, the time it takes, or whether I ride my bike up the hill or carry the bike up the hill. The energy will be the same. Next on our list is power. Now, power is the rate at which energy is expended. So power is given by this formula here, the change in energy divided by the change in time, which I could express as the change of time depending on the change of energy divided by power. Which means as the power increases, the change in time decreases. Here I see two identical pictures of a rider preparing to ride his bike up a hill, and the mass is the same in both cases of the rider and the bike. The force of gravity is the same. The height of the hill is the same. If I multiply those together, then of course the total energy needed to climb the hill is the same. I apply power in the first graphic and more power in the second. In the bottom picture, because I applied more power, the time decreased and I got to the top of the hill faster. Next is pressure. Pressure is the force exerted on the surface of an object, or the force exerted per unit of area. We all know of a barometer expressing ambient barometric pressure. At sea level, ambient barometric pressure is 14.7 pounds per square inch, and perhaps this graphic here will help you understand. We have a block here that weighs 14.7 pounds and it is spread out over an area of 1 inch by 1 inch. Next is torque. Torque is a turning force applied at the end of an arm. And here is a familiar looking torque wrench. This happens to be a Park torque wrench, one of the really nice ones. And here's a bunch of fittings that you can put at the end of the torque wrench. And the last on our list is vector. There are two ways to express quantity. First is a scalar quantity, which indicates only magnitude. Here we see a globe. That's an airplane over the Atlantic Ocean, and it's flying at 500 miles per hour. That is its speed, which is a scalar quantity because I'm not saying what direction the airplane is traveling. The other is a vector quantity, which indicates both magnitude and direction. So here's our airplane again, also 500 miles per hour, but I'm indicating with this arrow that the airplane is flying in a particular direction, in this case due east. And that arrow turns our scalar quantity into a vector quantity of velocity. That completes our basic list of terms and definitions. Many of these will be gone into in greater depth later in the video.